Okay, let's continue our discussion of soil deformation. And last time I told you about the modulus of deformation as being a very useful concept. So modulus of deformation. And I wanted to start by reminding you of these very important equations that govern the theory of elasticity. So we'll write them again. Epsilon xx equals 1 over E sigma xx minus nu sigma yy plus sigma zz. Epsilon yy equals 1 over E sigma yy minus nu sigma xx plus sigma zz. And then epsilon zz equals 1 over E sigma zz minus nu sigma xx plus sigma yy. These are the normal strains associated with the normal stresses, and you remember that the stresses in the perpendicular direction do influence the strains as well as the one in the major direction. We also have the shear strain, gamma xy equals tau xy over g, and gamma yz equal tau yz over g, and gamma zx equal tau zx over g. And I mentioned that we had a relationship that g was equal to E over 2, 1 plus nu. So that in essence, this theory of elasticity is based on two parameters, the Poisson's ratio, nu, and the modulus of deformation, E. One thing I wanted to mention is that when we solve problems in engineering in general, we have two types of equations. And these equations are, the first type is what I would call fundamental equations. So these fundamental equations are equations that are valid no matter what type of problem you deal with. They don't depend on the material. You can write them in a general term. So examples of this are equilibrium equations, or conservation of mass, and so on. They're not the only ones, but these are examples. So you can see that when you write the equilibrium equation or conservation of mass, it doesn't matter what kind of material you deal with, these equations are always valid. And then we merge with this what I would call the constitutive equations. And these equations describe the material behavior. So so examples of this is the elasticity equation. So for example, elasticity is one of them. Darcy's law, you remember Darcy's law from flow of water through soil, but we have others like plasticity theory and so on. And these are equations that describe the material. So they will they will, these constitutive equations would have different values for concrete, for steel, for soils, for marshmallow, or whatever. They have a soil property in them. And typically, we write those, we merge them, and that leads us to the governing differential equation. Why differential equations? Because typically, when we want to solve an engineering problem, we zoom in at the element level, and we write these equations at the element level. And so that element is dx, dy, dz, and then that's where the differential equations come into play. But so obviously, these equations of elasticity would be constitutive equations. All right. I mentioned that these are very, very powerful equations. They really help a lot in solving many of the problems. One big issue is that the soil modulus, E, depends on many factors. And I'm going to discuss some of those factors. And the factors that I'm talking about are of two sorts, basically. You have the state factors, and then the loading factors. But before I get to discuss this, I want to ask the question, soil modulus which one? And the reason this is an important question is that this modulus is associated with a non-linear curve. So we have to be aware of, and I'll take a sigma and epsilon representation, understanding that, as we mentioned in the last lecture, the slope of that line is not the modulus unless you run an unconfined compression test. So let me show a curve first, and you can, in this curve, let's say we have some cyclic loading, like this, several cycles, and then we go back. So you can see that there are many different moduli that can be associated with this. First of all, you have the initial slope here. So that's the, we typically call this an initial modulus associated with that slope. I'm not saying the slope is, but, and then you have something that we call secant modulus, because it cuts through the curve up to a certain value of strength. Then we have another one that would be what we call a tangent modulus. So this one would be associated with the slope that is tangent to the stress-strain curve at some point along the loading process. And then you have the unloading modulus, you have the reloading modulus, you have the loop of the cycle. These are cyclic moduli. So it can be an unloading, a reloading, it can be the loop of the cycle. You can see that there are many types of definitions. So if you receive a report from a geotechnical consultant, and the report says the modulus of the soil is 10,000 kilopascal. The very first question to ask is, which modulus are you talking about? And that's an important question, and then you keep that in mind so that you see whether it's an initial, a secant. If it's a secant, at what strain level? So these are important questions to ask. But let me go back to what I said here and talk a little bit about the state factors. So state factors means that what are the states that the soil is in? For example, state factors, density. Obviously, if you have a sand, and if the sand is very dense, then you're going to have a much higher modulus than if the sand, even though the grain size distribution may be the same, if the sand is loose, then you're going to have a much lower density, a much lower modulus. So as I'll say E increases as gamma dry, let's say, increases. All right. Another factor is the structure, the way the particles are organized, but the over-consolidation ratio. And we haven't described this. We'll get to this. So this one is typically in as an acronym is OCR. So the C over consolidation ratio, OCR. And this is associated with the highest stress that the soil was subjected to in its history divided by the current stress. So you have some soils, and I think I mentioned it before, where 10,000 years ago we had an ice age on our planet, and Chicago was under about 300 meters of ice. And so that was very heavy on the soils in Chicago, and now the ice is gone, but the soil remembers that it used to be under 300 meters of ice, and so if you, essentially the soil in Chicago is pre-stressed, the term that we use in concrete. The soil is pre-stressed or over-consolidated. Pre-stressed is the word we use in concrete, over-consolidated is the word we use in geotechnical engineering. So you can imagine that if you had these 300 meters of ice, the same soil under 300 meters of ice for many years versus the same soil under 0 meter of ice for many years, you're going to have a difference in modulus. So if OCR increases, then we're going to have E increases as OCR increases. And we measure this over-consolidation ratio in a number of ways, the most common way being through the consolidation test. Water content is also important, particularly in fine-grained soils. Water content, W. Particularly for fine-grained soils, I'll put fine-grained here. You can imagine that if the material dries, it becomes hard. And as a result, E increases as W decreases. And we talked about this before. It's due to the water tension that develops in the soil, in the pores, as the material dries. You know, we talked about the fact that if you take a piece of soft clay and you put it on the table, and then you come back tomorrow, it's going to be a lot harder tomorrow. Why? Because in this room we probably, we have air conditioning, so we have about 50% relative humidity. There's a lot of room for the water to go into the air. And this low relative humidity is attracting the water that's in the soil. At the same time, the silica in the soil or other minerals is attracting the water. And so the water is sitting there, and the relative humidity in the air in the room says, come over. And then the silica particles and the minerals say, no, no, you're not going anywhere, I want you to stay here. So the water is pulled in tension between these two mechanisms, and that tension is actually drawing the particles together. And that tension can be extremely high. You know, water has a tremendous amount of tension resistance, and so it's able to really attract particles. So that's why when the water content goes down, particularly in fine-grained soil, the modulus will go high. And as an example of application, compaction, for example, if you do compaction, and you have to do compaction as we talked about before, you do compaction on material has a certain water content, the optimum water content, but if you let it dry in the sun and the material becomes stiffer, it could crack as well because of shrinkage, but it becomes stiffer for that reason. You can't really rely on that increase in modulus, increase in stiffness, because if it starts raining, you lose the water tension because it's just too much water coming in, and then your modulus comes down again. So you have to be careful what is reliable. This certainly over-consolidation ratio is quite reliable, the density is reliable. This one is sometimes, and we call it apparent cohesion in the shear strength business. So be careful with that one. What else do we have? Water content, over consolidation. These are the main factors, main state factors. Okay. The other factors that I want to discuss are the load factors, and I'm going to keep this in here because we're going to come back to that. But the other factors are the loading factors. Loading factors. And what do I mean by loading factors? Well, first of all, if I draw a stress-strain curve like I've done here, and I put sigma versus epsilon. So that could be a simple shear test, Traxel test, whatever. And in here, I have the stress-strain curve. And this being soil, that stress-strain curve is highly nonlinear. The first influence factor that I want to acknowledge is the strain level. So we're going to first talk about strain level. The strain level makes a difference because if you deal with a foundation problem, foundation, the strain level in foundation engineering is typically of the order of 1%. Delta H over H. That's the order of magnitude. And so at 1%, you're in here somewhere. And you're looking at a curve that's going to intersect the epsilon axis at 0.01, 1% strain. So I'm going to be looking for a modulus that's right there, associated with that stone. If I deal with pavement design, then I'm going to be dealing with much lower strains because I've got so many cycles, so many trucks, so many cars that come and load the soil repeatedly that I cannot afford to have the type of strains that I would have in foundation engineering, where typically on a building like this, we would have one loading, the monotonic loading, and then we're done for 50, 100 years. So in pavements, we have a lot of cyclic loading, and we could not afford to start at 0.01 because we'd end up with a mess in no time flat. So in pavements, we're going to be operating at much smaller much smaller strains, typically 1/10 of this, if that much. So and sometimes we have embankments that we build next to rivers, and the material is relatively soft, the embankments is fairly high. There's a significant amount of settlement. You know, we talked about, in the last lecture, we talked about the Washington Monument settling about this much. Now we're talking about some serious strain. Now this was not intentional, and you don't want to design foundations to that large strain, but there are some embankments that settle several meters when you have to build them. And of course you build them, you wait for the settlement, and then you pave once the settlement is almost gone. So you could have some cases where you're actually operating at much higher strain. So the strain level is very important. Then we have the stress level or confinement level, which has a big impact on the modulus as well. For example, if you, so the second, we'll talk about stress level here. So I've got a stress strain curve, and I do a first test, sigma, as a function of epsilon. And I do a first test with sigma 3 equal to 50 kPa. It's a drain test, sigma 3, 50 kPa. And then I do another test with sigma 3 equal 200 kPa, let's say. Well, as you can imagine, the material is going to be much stronger, much stiffer because of the increase in confinement. So these would be traxel tests, let's say. So the confinement would be much higher. Obviously, the modulus that I'm going to get from these two curves, same sort, from these two curves, even at 1%, will be significantly different, even though I'm at the same strain. So the strain has an impact, but also the stress level has an impact. So we need to acknowledge those two things. Going on to discuss other things, the rate effect. The rate at which you load the soil. If you can imagine that right here, I'm loading the soil, and so I've got sigma versus epsilon again. And in one case, I load the soil, I do a very slow traxel test, and I load the soil in, say, 10 months. Okay? Very, very, very slow. And then, right here, I do another test, and I bring it to failure in 0.001 second. And boom! Well, you can imagine there's going to be a difference, okay? And so if I'm going to take the modulus at 1% strain, then that's going to make a difference. Same sort, same confinement, same strain level, different rate of loading. 10 months, when we do calculations of settlement, Tower of Pisa, been around 900 years. Well, that's a long-term modulus that we would need to predict the behavior. But if we are doing the pavement loading, for example, you know, a car traveling at 100 kilometers an hour, that's not going to stay on the load, apply the load for very long. Or if you lose control of your car and you hit the guardrail, on the side, the post is going to be pushed in a few milliseconds. So now the rate of loading has an impact. This impact is not that large, actually, because soils are not very viscous. You have some materials that are much more viscous, and so bitumen, for example, is very viscous. water actually is quite viscous. But the soils are not very viscous. So you have to have, that's why I said 10 months was just a millisecond here. That would make a big difference. But if you have a 10-to-1 ratio, that's not going to make that much difference. Nevertheless, that is a factor. So here's another one that needs to be considered is number of cycles. Number of cycles. You can imagine that if I take a soil sample and I do a triaxial test or any other test, and I start loading the sample, and if I were to continue, it would go on something like this. But here I say, oh, wait a minute now, I've got a platform that's going to be subjected to a lot of hurricane waves, maybe 1,000 of them. Then I'm going to have to simulate this by doing some unload, reload cycles. Or I have a pavement that I'm going to be loading for 2, 5, 10 million loading cycles during the lifetime. And you can imagine then that the modulus associated with one cycle, like a building, boom, you put it down, you leave it alone, will be very different from the modulus that will be associated with 1,000 cycles, 1,000,000 cycles, and of course, in here, the amplitude, not just the number, but the amplitude of the cycle. If you're right here, maybe you won't make that much damage, but if you start cycling here, you're going to lose the soil in a hurry. I mean, you're going to fail it in a hurry if your amplitude is fairly large. So these are important factors. And I didn't quantify, I discussed a little bit, but I didn't quantify this. So it's important, again, when you get a modulus, a soil modulus, that you ask the question, what is the strain level? What is the stress level? What is the rate effect that you're giving me? What is the number of cycles that you're giving me, so that you get a good feeling of what this modulus is going to represent. And unfortunately, or fortunately, you can look at it the way you want. The soil modulus is very complicated, and it's in a way that's what makes geotechnical engineering needed in the business, because they have to decide from their experience, their knowledge, and their background what that modulus is. And certainly, having said all this and doing all this testing and understanding the theory, you also have to have tremendous experience and judgment, because the more you have seen case histories and how they work and how they behave, the more you can estimate these numbers with a lot more reliability. All right, so these are the things. So remember to ask those questions whenever somebody gives you a modulus. I wanted to go back, and maybe I should have started with this, but let's go back to these equations and practice a little bit through an example. Practice how to calculate modulus when you get a test result. So let's say that we have a soil sample, and we're going to test that sample in the following way. We're going to take a container. It's a cylindrical container, and there's a bottom. And we're going to put the soil sample in it. So here's the soil sample. And then we're going to put a platen on top of it, and we're going to apply a load. Okay? So this is going to be sigma z. And under this load, that's the steel platen. Under this load, the material is going to be squeezed because we allow water to drain out. Okay, we're allowed to, this is called the consolidation test. All right? So the consolidation test, the water is squeezing out of there, and that's why you have settlement. So water squeezes out of there, and it's also, you can drain it at the bottom as well, and that's what makes the deformation take place, because if it's saturated, otherwise there wouldn't be much deformation. So again, you get here delta H, and you had an initial height H, and so epsilon ZZ is going to be equal to, so epsilon ZZ equals delta H over H. Okay? But you also have sigma XX, sigma YY, epsilon XX, epsilon YY. What do you think of epsilon XX and epsilon YY? This is made of steel right here. Well, that steel ring is not moving. So the strain in XX and YY is going to be 0. Let's look at those things now. So if I look at this and I say, I'm going to take this element and I'm going to write those equations. So the first one is valid. I write epsilon XX. I'm going to start with epsilon ZZ because that's the main direction of loading. So let me do epsilon ZZ equal 1 over E sigma ZZ minus nu sigma XX plus sigma YY. Whoops. Yes, I need to. And then I can write that sigma XX is equal to sigma YY, right? Because in this direction and that direction, this is a cylinder, so they're the same. I can also write that epsilon YY. Well, let me do it in parallel. So epsilon XX. Epsilon XX is equal to epsilon YY, and because the steel is not moving, that dimension doesn't change as I load the material, so these two are equal to 0. Okay? If I take this expression right here, and I set epsilon YY equal to 0, epsilon YY is 1 over E, sigma YY minus nu sigma XX, same as sigma YY, so another sigma YY, plus sigma ZZ. Okay? And this is 0. So therefore, sigma YY minus nu sigma YY minus nu sigma ZZ equals 0, and therefore sigma YY is equal to nu sigma ZZ over 1 minus nu. Okay. So that's what I get so far. Now I go back in here and I write that epsilon ZZ is equal to 1 over E sigma ZZ minus nu, and I'll have 2 of those because they're the same. 2 nu sigma YY, which is nu sigma ZZ over 1 minus nu. So therefore, so therefore E, the modulus, is going to be, I'm regrouping all this, sigma ZZ over epsilon ZZ times, what do I have in here? I have 1 minus 2 nu squared over 1 minus nu. Okay? I just wanted to show you this so that you can you realize that you can obtain this modulus of deformation from this test. Now, the the curve that you get from this test will be sigma versus epsilon. And if you were to plot that curve, you would see that it actually looks, on natural scale, it looks something like this. And it curves up. And we'll come back on this. This is the influence of the ceiling. But you could take a point on that curve, right here, let's say, and put a straight line on it, and you would have a sigma ZZ right here, and epsilon ZZ right there, and you just go in there, and then you estimate nu 0.3 to 0.35 for the drain Poisson's ratio, and from this test you can get a modulus. Again, you have to be careful to be at the right value of epsilon and so on. All right, let me then go to some how to estimate the modulus, because in the end that's what's necessary. And the modulus values that I'm going to give you are typical soil moduli. So moduli or modulus values for loading that is, so I'm going to give you epsilon about 1%, stress level, I'm talking about foundation engineering basically. So stress level, foundation engineering, maybe 100 kPa. Rate effect, 1, monotonic loading, monotonic, and then permanent loading. So there's no cycles or rate effect, no cycles. Okay, so with those caveats, what I can tell you is that in clays, you're probably looking at moduli that are about 120 times the underage shear strength, and about 700, even though we don't do it, we don't do the blow count in those materials typically, and about 3 times the Q sub C value from the cone penetrometer. In sands, I would say that the E value is going to be about 1,000 times the row count from the standard penetration test, and also about 3 times the cone penetrometer resistance. So these are orders of magnitude. You definitely, considering the complexity of this number, the modulus of deformation of soils, these are all, only a first estimate. You're in the field, you say, okay, what kind of settlement can I expect? You can use some of those things to get a feel for it, but you must measure this particular parameter because it's very important to do so to have anything reasonable. So that you have the triaxial test, which is a good way of doing it. We will talk in the next lecture about the consolidation test, but I wanted to finish this discussion by talking to you a little bit more about a test that's really well suited for measuring the modulus of soil, and that's called the pressure meter test. So I got about about 10 minutes left. And let me then discuss a little bit what this test is all about. So, pressure meter test. Pressure, whoops. Meter test. It's a test that was invented about 50 some years ago, and it consists of drilling a hole in the ground, and lowering in the open hole. So the hole is about that big around, about 75 millimeters, and in the open hole you lower a cylinder that can be expanded. It's a probe that is about that long, and again about the same diameter, and the hose that goes from the probe to the ground surface. So let's say that you're in here, and you have this probe that's in the ground, and it goes here to a pump, basically, and once in place, it goes in deflated, and once in place, you inflate that membrane, and it inflates horizontally. I'm exaggerating because actually it doesn't inflate that much. And then you measure the increase in radius, delta R, for a given initial radius. So the blue probe here has an initial radius 2R0, or initial diameter, that's 2R0. And then you plot a curve. As you expand, you measure the pressure that's generated against the wall of the borehole, pressure P. And delta R, so you measure here the volume, basically, and the pressure on the gauge. So the volume of water that you inject in the probe is measured, and from the volume injected, you can back calculate the relative increase in radius of that cylinder. And then you plot a curve that looks like this, P versus delta R over R0. It turns out that this, by definition, is the hoop strain. Okay, so it's a strain. And then this one is the radial stress. So this is sigma R, and this is epsilon theta. So you do measure a stress strain curve in the soil. And this stress strain curve looks something like this. And you know, at first, the blue probe doesn't touch the green hole, so there's a gap, and so the blue probe expands and finally touches the hole, and then you get into the linear part of the behavior. Right here, you have a slope from which you're going to get the modulus. Right here, you have a yield pressure, which will be very useful because you want to keep the loading of the foundation below this yield pressure so that you minimize the amount of creep and long-term movement that you're going to accumulate. And then right about here, you have what is called the limit pressure of the soil. So in the end, you obtain a profile, because you don't run just one test, but at a location, you will have a number of parameters. So I'm going to put several here. The two main ones being the modulus. We'll call this E0. First load modulus, so the pressure meter. So this will be E0. And then we will also plot PL. So you get some values that are right here, right here, right here, right here, right here, and then you get a profile of strength of the material, and then you get something similar for the limit pressures and so on. This is one of the rare in situ tests that actually gives you a modulus that is directly measured. And typically, when we use this in foundation engineering, we will, in foundation engineering, remember I told you there are two cases, bearing capacity and settlement. And when it comes to bearing capacity, we will typically use P sub U approximately equal to PL. And then we use a settlement equation that is of the form, at least for rectangular footings, I'll put 0.8 1 minus U squared P V over E. So S is the settlement. S is settlement. Nu is Poisson's ratio. E is modulus. P is foundation pressure, the pressure that exists between the foundation and the soil. And B is the width of the foundation. So let's say, as an example, that we have a modulus E of 10,000 kilopascal. That we have a footing that has a width of 3 meters. That we have a pressure on the footing of 150 kilopascal, and that Poisson's ratio is equal to 0.35, and that it's a rectangular. This number here is a shape factor, so then we would get S equal 0.8 1 minus 0.35 square times 150 times 3 meters. And if we want the results in millimeters, I'll put 3,000 here, and then divided by the modulus 10,000 kilopascal. So I don't know what that is, but that's how we would calculate the settlement. And if you, so this is what I would call an analysis case. But if you had a design case, if the question was, how big should the footing be? If I have this much load, given the load, then you would have to set the settlement. Maybe the structural engineer says, I don't want any more than 20 millimeters of settlement. So you're going to stick the value of the settlement right here. And then you have 0.8, you know Poisson's ratio. The pressure is going to be the load divided by the area. So B squared, let's say if you have a square footing. So load divided by B squared multiplied by B. We have load divided by B. And then E is here. You know the load. B is the unknown. And then by design, you can calculate B to be able to satisfy the settlement that is required in this case. But again, the modulus right here is the most important number, and that's the one that's critical, and that's why soil deformation is a very important topic. Thank you.